picking up with Lenz's law, we can say that we are now talking about two distinct fields. Now, Lenz's law says that a current produced by an induced electromotive force moves in a direction so that the magnetic field created by the current opposes the original change in flux. Okay, we're now discussing two distinct fields. We're discussing both the changing magnetic field or flux that induces a current, and we're discussing the magnetic field produced by that induced current. So the second field opposes the change in the first. Let's go back to our last example to talk about this a little more. So if we go back to our last example, what is happening here is that a uniform magnetic field is turned on. So we go from having zero field through this coil to having some final field through this coil. And I'll just pick a direction. We know that it's perpendicular to the plane of the coil. So since that field turns on and we go from 0 to nothing, what is going to be induced is a current that produces a magnetic field that opposes this. So if we use our right hand again, we can figure out that if that's the direction we're going to get an induced field, moving around the coil in this direction is going to be our induced current, and we can figure out that that's our direction of our induced EMF. This is actually captured in the negative sign of Faraday's law. So the second field opposes the change in the first. It's resistive in a certain way. So one application of Lenz's law is actually a pickup coil on an electric guitar. So the pickup coil, you've got a pretty strong magnet that magnetizes a portion of the metal string that you've got, your guitar string. And as that string vibrates, it moves closer and further away from the pickup coil. So it's going to create a change in magnetic flux. And that pickup coil is going to have a induced current that is related to and is at the same frequency of that vibration of the string. And it's going to go to the amplifier where it's going to be amplified and converted into a sound wave by the speakers in the amplifier. Kind of cool. Good example of Lenz's law in action. Okay, so our changing flux causes some current. How do we change our flux? Well, there are three ways we can change our flux. If we look at what our flux equation is, we can either change our magnetic field. So that might be the relative motion of a magnet in a coil, right? You might move your magnet closer to your coil so you get a stronger magnetic field through the coil. You could change A. So changing A, I don't have a picture of this here, but say we had a coil and we pulled on it and stretched it out in a way to change its shape. So this A is different than this A. So you could change the shape of your coil. You could also change the angle. So you could rotate the coil relative to a magnetic field. So all those things are ways to change the flux that would cause an induced EMF. And remember that induced EMF is going to be in a direction that opposes any change in the magnetic field. So if we want to solve any problems with Lenz's law, some of the things you're going to look for. You're going to look for, if you're going to produce a current, you need a closed conducting loop to have an induced current. You also need an external flux. So you need a flux from an external field through the loop that is changing in time. If it's not changing in time, we're not going to see any induced current. All right, so let's try an example of Lenz's law. This is kind of a wordy, long example, so let's see how we can do it. So we've got a 100-loop square coil of wire. Let's start highlighting things that we want to write down as our givens. We've got a 100-loop square coil. It's got a side length of 5 centimeters and a total resistance of 100 ohms. It's positioned perpendicular to a uniform, so we like that word perpendicular, to a uniform 0.6 Tesla magnetic field. It is quickly pulled from the field at a constant speed, moving perpendicular to the magnetic field in a region where the field drops abruptly to 0. At t equals 0, we're going to have the right edge of the coil at the edge of the field, and it takes a certain amount of time, so 0.1 seconds, for the whole coil to reach the field-free region. We want to find all this stuff. So the rate of change in flux through the coil, the EMF in the coil, the induced or current induced, how much energy is dissipated, and what was the average force required to do all this work. So much stuff. Okay, so let's write down what we're given. We are given, oh, that's bright yellow, that's not helpful. We are given 100 loops or 100 turns of wire. We are given that it is a square with side 5 centimeters. So you know what? I'm going to switch that to a lovely 0.05 meters. And since we're squaring it, we'll just do 0.05 squared, meters squared. Okay, we are perpendicular to a uniform 6 Tesla magnetic field. So where our field is, it's going to be 6 Tesla, or 0.6 Tesla, sorry. It's quickly pulled from this field at a constant speed, moving perpendicular, where it drops to 0 at time equals t. So you know what, I'm going to just draw this situation. So we've got our n turns of wire. We've got a field, so I'll give my field just x's, right? So this is my magnetic field. And it says at time equals 0, the right side of my coil is kind of at this region where we've got the 0.6 Tesla, and over here we've got 0 magnetic field. So it is being pulled in this direction with a constant velocity, and it takes 0.1 second for the whole coil to reach the field-free region. So that actually kind of tells us that our velocity, since this side is 5 centimeters and it takes 0.1 seconds, our velocity is this many meters per second, right? So we want to find the rate of change in flux through the coil. So we want to find this. So since we know that our velocity is a nice, easy, simple, reasonable, I can write steady velocity, we can write a delta instead of a d phi dt. Okay, so when we do that, we go from having, initially, we have a 0.6 times our area. So I'm going to write 2.5 times, let's write it a little differently. Let's write our final magnetic flux minus our initial magnetic flux instead of trying to write from right to left. So our final magnetic flux, we get into this field-free region. Our final magnetic flux is going to be 0 because our magnetic field is 0 when we're done. Our initial magnetic flux is this 0.6 for the magnetic field, and then 2.5 times 10 to the minus 3 meters squared for our area. And we do that in 0.1 seconds. So the change in our magnetic flux over time is going to look like just a simple negative 1.5 times 10 to the minus 2, and that's going to be in Webers per second. So the units of magnetic flux are Webers, that's WB, and that is just Teslas times meters squared is a Weber. Okay, so that's our first one, A, checked off. Let's go to our next one. So the next thing we want to do is we want to find, ooh, let's undo that. We want to find the EMF and the current induced. Okay, so if we look at that list of things that we wrote down on the last page as our given, we know that we can find our EMF as negative the rate of change of flux. And that negative sign, again, is because it's going to oppose this rate of change. So all we have to do, oh, and we need our factor of n in there. So all we have to do is our factor of n times the EMF we just figured out was, or the change in flux we just figured out was induced in each loop. I did not write that right. Sorry about that, guys. So the rate of change we had was a negative 1.5 times 10 to the minus 2 Weber per second. Okay, so our induced EMF looks like a negative sign and a negative sign, so we end up with a positive, and 100 times that 10 to the minus 2 just gets rid of the 10 to the minus 2. So we've got 1.5 volts. That is my answer to part B. So what about part C? Part C says how much energy is dissipated in the coil. Oh, you know what? We haven't found our current induced yet. So our current, let's back ourselves up. Got too excited that I got one part done. Our current induced, remember, we're going to induce an EMF, and Ohm's law says that our current induced is going to be proportional to the voltage applied or the EMF. So V equals IR becomes E, or epsilon equals IR. And we're going to rearrange that to get that my current induced is that 1.5 volts divided by this 100 ohm resistance that we're given, right? So we're going to use Ohm's law for that part. So our current induced is going to be 1.50 times 10 to the minus 2 amps. Okay, now I'm done with part B. So part C, how much energy is dissipated? So energy, you might remember, is how much power gets used in a certain amount of time. So power times time, right? So energy that is used is going to be the power that is used over how long is this power being used. So the average power being used, we can write in a few different ways for a resistive coil. So I'm going to write I squared times R, and then I'm going to multiply that by T for my energy. So we just figured out I squared, or I at least. So it's 1.5 times 10 to the minus 2 that I'm going to plug in there, and I'm going to square it. We are given R, we are given that 100 ohms, and we are given T at 0.1 seconds. So if I plug all of those things into that equation, make sure I'm in the right units with the right powers of 10, I get 2.25 times 10 to the minus third. And remember, units of power, or units of energy rather, are going to be joules. So that is part C. So then finally, we want to do part D. What was the average force required? So let's get ourselves another page to find part D. What was the average force required? When we are trying to figure out force, remember, we could use the work energy principle. So the work energy principle says that the energy that it takes to do something is either the work you put into something or the work that comes out of something. So we had to apply a force over a certain distance. We had to apply a force over the distance that it took to pull this coil out of the field, which was just the width of the coil, that 5 centimeters. So the force, we could take the work divided by the distance. Now we just figured out the work we had to do was the energy that was dissipated. So the energy that was dissipated was that 2.25 times 10 to the minus 3 joules, right? And we do this energy dissipation over a distance of 5 centimeters. So maybe instead of 5 centimeters, I want to get myself in the right units, the units that are reasonable, and 0.05 meters there. So if we take joules and divide by meters, we're going to give ourselves newtons. So we figure out that the force that was needed, or the average force that was required, was going to be 0.045 newtons. So that's 0.0450 newtons for my part D answer. And now that's an average force required because we're going over this distance. The actual force is going to vary as we get out of that field to keep it at a steady velocity. That is a good place to pause. We'll pick up with the EMF of induced on a moving conductor with the next video.